Get started on 262 notes. 262 notes. Our first example, they want us to compare the properties of each of the following two functions over the interval from 0 to 16. When we compare our properties, we're doing the same thing that we did in our previous lesson. We're comparing our y-intercept and our rate of change. The first part of this example, let's compare the y-intercepts of each function. Keep in mind, your y-intercept is always going to be 0, comma, y. If we take a look at function a, we're looking where this line crosses our y-axis, which would be right at this point. That point is right between 800 and 900, which means our ordered pair is 0, comma, 850. Our table, for function b, we're going to look for our 0 in our x column, which is here, and whatever value is next to that is going to make up our ordered pair for our y-intercept. Therefore, in function b, our y-intercept is 0, comma, 850. If we compare these two y-intercepts for each function, I think we can come to the conclusion that the y-intercepts are the same. The second part of example 1, we have to compare the rate of change for each function over the interval from 0 to 16. When we compare the rate of change, we have to use our rate of change formula from our previous lessons, also known as our slope formula, which is m equals y2 minus y1 over x2 minus x1. Our change in y over our change in x. Let's first look at function a from 0 to 16. At 0, we're at 850. And at 16, we're at 1,600. I'm going to go ahead and rewrite these ordered pairs over here off to the side. So we have room to substitute these in. We need to identify our x1, y1, x2, y2. And then we're going to go ahead and substitute these known values into our slope formula. When we do that, that's going to give us 1,600 minus 850 over 16 minus 0. Our y2 minus our y1 over our x2 minus our x1. If I take 1,600 minus 850, that's going to give me 750. And then if we take 16 minus 0, that's going to give us 16. When we take 750 divided by 16 in our calculator, we're going to get approximately 46.875. We're just going to go ahead and round that up to 46.88. So our rate of change for function a is 46.88. Let's go ahead and find our rate of change for function b from 0 to 16. So at 0, we're at 850. At 16, we're at 1,480.88. We're going to rewrite our ordered pairs. Before we substitute these values into our slope formula, we're going to identify x1, y1, x2, y2. We're going to take our y2 minus our y1. So 1,480.88 minus 850 over 16 minus 0. If we take 1,480.88 minus 850, that's going to give us 630.88 over 16. If we put this into our calculator, we're going to get approximately 39.43. 39.43. If we compare the rate of change of function A to function B, we need to keep in mind our rule. If we did have a negative value, we would have to take the absolute value of that. But for this example, that does not apply, so we can just go ahead and compare these two numbers right away. And we can see in red, that's representing function A. 46.88 is greater than 39.43. So we can say function A has a greater rate of change over the interval from 0 to 16. Example 2. A petri dish contains 8 bacteria that doubles every 15 minutes. Compare the properties of the function that represents this situation to another population of bacteria graphed below. That starts with 8 organisms. Let's go ahead and highlight 8 organisms over the interval from 150 minutes to 210 minutes. We're going to compare the y-intercepts first, and on the next slide we'll compare the rate of change. Keep it in mind, your y-intercept is always 0, y. If we look at our graph first, we're going to look to see where my function hits my y-axis. And it looks like it's at 0, 0, but what we highlighted at the end is that it informed us that it actually starts with 8 organisms. So our y-intercept for our graph is 0, 8. So after 0 minutes, we're starting with 8 organisms. Now we need to figure out our y-intercept for our other function. A petri dish contains 8 bacteria that doubles every 15 minutes. Out of those 3 that we highlighted, the one that's important to me is that it contains 8 bacteria already, giving us the order pair 0, 8. So both of these functions are starting out with 8 bacteria. From here, we can say that both y-intercepts are the same. All right, example 2, the second part of example 2. A petri dish contains 8 bacteria that doubles every 15 minutes. Compare the properties of the function that represents this situation to another population of bacteria graphed below that starts with 8 organisms over the interval from 150 minutes to 210 minutes. So now that we've dealt with comparing the y-intercepts, we're going to compare the rate of change for each function over the interval from 150 minutes to 210 minutes. We need to go back to our first sentence here in this paragraph. A petri dish contains 8 bacteria. So it started with 8 bacteria. It's doubling every 15 minutes. Looking at this first sentence, we are going to have to develop an exponential function from this. Because it's doubling every 15 minutes, that every 15 minutes is our interval over time. So we're going to deal with f of x equals a times b to the x over t. Our a is our starting amount of bacteria, which is 8. My b is my growth or decay factor. In this case, it's a growth factor of 2 because it's doubling. And then we have to the x over 15th power. We're talking about our interval from 150 to 210 minutes. We've dealt like problems with these before. We are going to have to substitute 150 into our function and get our output value, and then 210 into our function and get our output value as well. So when we do that, f of 150 equals 8 times 2 to the 150 over 15th power. We are going to have to put that in our calculator. So when I put this in my calculator, that is going to leave us with 8,192, giving us the ordered pair 150, 8,192. We're also going to have to input 210 into our function and get our output value. So when we input 210 into our function, we're going to put this into our calculator, and when we put this into our calculator, we're going to get f of 210 equals
131,072. I'm just going to put these vertical lines here to separate our work so it doesn't get too messy here. This function gives us our order pair 210, comma 131,072. So we have our two order pairs. Now we need to determine our rate of change using the slope formula. This is going to be my x1, y1, x2, y2. We have our slope formula, which is y2 minus y1 over x2 minus x1. If we substitute these values into our slope formula, we're going to take 131,072 minus 8,192 over 210 minus 150. If we put this in our calculator all at once, so I'm going to take 131,072 minus 8,192. I'm going to put that in parentheses. I'm going to divide it by 210 minus 150, and I need to put that in parentheses as well in my calculator, and we'll get 2,048. This time we do have units. Our units for this is going to be 2,048 bacteria per minute. So that is our rate of change given the information in our word problem. Now we need to determine our rate of change given our graph function, and then we're going to compare the two. So our first order pair from our graph function is 150, comma, we're going to go ahead and look at our graph at 150. It looks like it goes from 200 to 400, so right between 200 and 400 would be 300. I would say that's slightly below 300, so we're going to call that 275. And then we have 210, comma, if I go to 210, see where it hits on my graph, that hits right about 1,000. We're going to go ahead and substitute these values into my slope formula, but before we do that, let's identify x1, y1, x2, y2. We're going to take y2 minus y1. 1,000 minus 275 over 210 minus 150. When we put this into our calculator all at once, 1,000 minus 275 in parentheses divided by 210 minus 150, we're going to get a decimal of about 12.083 repeating, and we're going to go ahead and round that to about 12. So we're going to use our approximation symbol, and we're going to round that to about 12, and that's also going to be bacteria per minute. Now, when we compare these two rate of change, we need to keep in mind that if there was a negative value, we do have to take the absolute value before comparing the two. But here, these are both positive values for bacteria per minute. We have 2,048 and 12. Comparing the two, we can see 2,048 bacteria per minute is a greater rate of change. So we're going to go ahead and say the scenario function has a greater rate of change over the interval from 150 minutes to 210 minutes.